Okay, let's look at risk assessment in a little more detail. We've covered some of this in the PowerPoint slides, and I know some of this will be a review, but it's worth going over. Really, the calculations for risk assessment are quite simple. It's finding the correct numbers to put into those calculations that can be quite tricky. So let's recall that if we have risk, in order to have a risk, we have to have two things. We need to have a hazard, and we need to have an exposure. So let's take sunshine and the ultraviolet rays for the sun. Those pose a hazard, right? But it's not a risk unless there's both hazard and exposure. So you have to walk out there and have exposed skin to actually have a risk from sunburn. So just the sun in itself is only a hazard. And the same is true of other chemicals, of other issues, I should say, such as chemicals, which can form toxicity. So let's talk about toxicity. That's going to be what we talk about the most. Those are the most complicated ones. There's several kinds of toxic chemicals. Carcinogens, mutagens, teratogens, which cause birth defects. These are all different kinds of hazards that come from chemicals. There's also just plain chemicals that can make you ill by affecting your digestive system or by giving you chemical burns on your skin. In addition, there are certainly physical hazards. Like we mentioned, the ultraviolet rays of the sun, there's explosion, heat exhaustion, floods, corrosion. These are all hazards. Then there's environmental hazards. They're similar to the toxicity problems, but we're talking more about aquatic toxicity. So toxicity to fish and frogs and phytoplankton of the water. There's avian or bird toxicity. So it depends on whether you're talking about humans. Most of the work we're talking about today will be about humans and the EPA's toxicity issues, but there's certainly a lot of work done on aquatic toxicity. And then there are big picture hazards: acid rain, global warming, ozone depletion, security of water, and political security. All of these are hazards on a grand scale. Let me try the eraser here and see if I can move on. Good. So one message that the book tends to keep pounding on is that pollution prevention is the best way to reduce hazards. Many pollutants are toxic to people and ecosystems, and especially man-made chemicals that we've used to make different products. So to avoid risk, pollution prevention is always better and more efficient than cleanup after the fact. That's just kind of common sense. But the fact is, there is a lot of chemical pollution out there already, so we have to worry about the hazards and the risks. So ethics is a big issue. Sometimes the risk isn't apparent. Products are popular. The chemicals stemming from those products are not well understood, but the economic driver to get these products out there will tend to get them out there. There are agencies like the EPA, the Food and Drug Administration, that are watchdogs, but sometimes they are underfunded or just don't have the time to cover as many things as they could, and so things can happen and things can be released. So let's get into the risk assessment then. So risk assessment really is comprised of 4 components. Hazard assessment, that's really just going through the papers and the literature and the reports and trying to see if a chemical, for example, really does pose a hazard. And believe it or not, there's a lot of literature out there on this. People study this, toxicologists, epidemiologists, lots of people, aquatic ecotoxicologists look at chemicals and do experiments with usually with animals to try to see what levels are harmful. If something is determined to be a potential hazard, then the next thing is also to look and see what the dose response assessment of that chemical is. In other words, how much of it does someone have to be exposed to for there to be a problem? And we have to think about how they might be exposed to it. Are they consuming it, maybe drinking it in the water? Are they eating it? Are they breathing it? Or are they being exposed to it dermally on their skin? And then after that's determined, we would determine, okay, to what extent are they actually being exposed? So say it's bad air at work. How often are they at work? How much does the average person breathe in a day? These sorts of questions. Once you have those first three things, you can then start to put the numbers together and actually characterize the risk and see whether it's acceptable or not. So as I said, hazard assessment means examining the evidence to see if there's a legitimate human or environmental health concern. So there are sources of information, toxicity studies. These are lab studies on plants or animals, and very valuable information is epidemiology. There are cases where humans have been unknowingly, or in some bad cases, knowingly in sort of war situations, exposed to certain chemicals. So unfortunately for some chemicals, we have actually human evidence of what these chemicals can do for you or do to you. Then the dose response assessment kind of goes hand in hand with that, because it's usually pretty quick to determine whether there's a potential health concern. And then the question becomes, how potent is the hazard? So this means figuring out how much ingested or breathed or touched would cause a problem or be likely to cause a problem. So here's an example. This is mostly ends up just being kind of unit conversion problems, but you're really kind of paying attention to what kind of subject you're working with, whether it's an adult, a male, or a female. In this case, let's say there's a city drinking water crisis, and the water contains 3 milligrams per liter of nitrate, which is not a whole lot, but it's still a significant amount of nitrate. And you'd say, what is the daily dose for females, males, and children of the city? So there are standard assumptions we make so that everybody's kind of calculating the same risk, and these are enumerated in some of the tables in your book. In one, for example, how much water does a person drink a day? Adults would be credited with 2 liters per day. Children would be only 1 liter per day. Males are generally larger than females, so an average male would assume to be 70 kilograms, the average female 50 kilograms. And then children, of course, it can be highly variable as to how old that child is, but for the sake of uniformity, the child is assumed to be 10 kilograms, so we're talking about a fairly small child here. So the absorption efficiency of the human stomach or intestinal wall, so this is physiologically how much nitrate is able to pass through the stomach and intestinal walls and into the bloodstream, is 15%. So pretty rough numbers, pretty average numbers. And with that, you would figure out the dose. So the female dose would be the 3 milligrams per liter, that's the concentration in the drinking water, times 0.15, that's the 15%, times 2 liters per day, that's how much water is drank by a female, and then divide that by the 50 kilograms, because we want to know how many grams of nitrate is being ingested per kilogram of person per day. So if you check those units, you would see that that's 0.018 milligrams per kilograms per day. And the exact same calculations carried down through for a male. You see the male has a smaller dose, even though he's drinking the same water, the same amount of water, but he's larger, so it's a lower dose per kilogram. And then the child, by the same token, is quite a bit larger, because it's just a small child drinking. Even though the child is only drinking half the water, it's a large dose compared to the adult. It shows, kind of spotlights the vulnerability of the children. Okay, so now let's look at continue to look at the dose response in terms of what kinds of information is available out there. So the dose response curves would be that now that you know the dose, you want to know whether it's enough to elicit a negative response or a toxicity response, a sickness or carcinogenic response. So this is worked out in lab or epidemiology studies, as we mentioned. So most likely it's going to be in the lab. There's just so many chemicals out there, and not too many of them have true human exposure tests. The tests are uncertain. Why? Well, they're not performed on humans, right? And they're mostly performed on mice and rats and aquatic animals if you're worried about ecotoxicity in the aquatic environment. But usually they're worked on mice or rats with humans and trying to extrapolate to the human behavior. And they're hard to, the epidemiology studies are hard to control completely. As you can imagine, people have different ethnicity, different genetic background, different diets. Some may have smoked or drink, so that it really kind of clouds the evidence as to how much one particular chemical is being harmful or not. That being said, these studies do exist, and they typically look for the probability of an adverse effect as a function of the dose. And so in a perfect world, you get a linear response where the more the dose, the greater the adverse effect. And this is gives you a slope factor, which is the potency. So the steeper the slope, the more potent this chemical is. Poison, if you will. Maybe it only makes you sick at low levels, but if you get to a certain higher levels, it could actually cause fatality. This can also have these are a little messy, these plots, but if you look at this plot down here, the little one that I've drawn in, it's also linear, but you notice there's just a little difference in this one, in that there's a kind of a behavior at the beginning where nothing really happens. This is known as a threshold. There's just no adverse effect below that dose. And so this is quite common, where at certain low levels there's just no noticeable effect, and then it hits a certain threshold and there's an effect. So a key concept as we go forward is there's no such thing as a threshold for carcinogen, but for non-carcinogens, where you're talking about illnesses or irritation of the skin, these sorts of things, there often are thresholds. Carcinogens are either risk of cancer or no risk of cancer. So let's look at the slope. The slope in this case, if we have the probability of some bad response, and so that would be, say you tested 100 mice, and at a certain dose 10 out of the 100 mice died, for example, then at that dose there would be a probability of 10% of some adverse effect. So the x-axis is dose, so that's something like milligram per kilogram per day. So slope is actually the inverse of the milligram per kilogram per day. If I can get so this is the slope value. So we interpret the slope as the potency or slope factor, or an estimate of the probability of harm or health effect increasing with the dose. And the steeper the slope, the higher this value, the more potent is the risk, the hazard of this chemical. Okay, let's move on to exposure. So exposure is probably, the ones before this were kind of ecotoxicological, biochemistry. They're typically not what environmental engineers are going to be working on. Environmental engineers are going to use those numbers. But where environmental engineers are going to work, and where they're going to take advantage of their knowledge of the environmental chemistry, the environmental fluid mechanics, is the exposure assessment, estimating how much exposure would be happening under different circumstances. This might be in a workplace, this might be in a home, this might be just in general walking around on the planet. Sorry about that. So what we need to know when we're doing this is, what are the sources of the chemical? What are the pathways to exposure? Is it through the air? Is it through water? Is it concentrated in the food supply? We want to know the dose. So what are the levels? What are the concentrations? We want to know the frequency. So how often do you drink it? How much do you drink each time? We want to know the uncertainty, because this will also translate into the risk. And we want to know if there's differences in population, So you can't just use the same numbers for everybody. So maybe hazards with air quality might be higher for exposures of urban people versus rural people. Although we know that's probably not the case around here because we have some of the worst air quality in the country. And that takes us to the final step. So once we know that there is indeed a hazard and we know roughly how potent the hazard is, and then we can start to piece together how much a person has been exposed or a fish has been exposed, we can combine those three steps into a risk estimate, and that's what we call risk characterization. So a formal approach is different. It's a key point here. You do it a little bit differently for a carcinogen and non-carcinogens. And also, once you get into probability, it's a little bit interesting and a little bit hard for sometimes the general public to appreciate this, but there is actually formally an acceptable risk. I know that sounds a little funny, but let me explain it. An acceptable risk means it's 1 in a million or less. So it's numerically it's 10 to the minus 6th. So if I find that the risk of a hazard is less than 10 to the minus 6, it's not worth worrying about, and legally it won't be worried about. So what this means, and if you needed to explain it really to someone who did not have much of a background, you might say something like if 1 million people were exposed to the chemical at the acceptable level, one of them would suffer the adverse effects. And that's, that's not fun to think about for that one person in 1 million, but you have to be realistic. There is a finite amount of chemical out there. People are being exposed. And if you're worried about everything beyond that, beyond the 1 in 1 million, you would never get anywhere. And in fact, there are people who argue that 1 in 1 million is far too conservative and really opens us up to a lot of legalities and a lot of impractical problems that we can't solve. But be that as it may, we are the engineers, and to us, if it's 1 in 1 million or less, we don't worry about it too much. We call this the de minimis risk. So it's too small to quantify or worry about. It's probably swamped by the hazards of walking across the street in a busy traffic setting. So that being said, let's move on to the techniques for first for the carcinogen. Trying to erase. Sorry, I'm clumsy with this thing. There we go. So let's move on to the carcinogens. So for carcinogens, an acceptable concentration. We'll talk first about drinking water. So this changes a little bit for whether you're breathing or drinking or eating, but let's do one that's familiar to us all right now, drinking water. So to calculate what an acceptable concentration of a chemical that is a known hazard, we would say that the acceptable risk times the body weight times the averaging time divided by the slope or the potency factor here times the IR, which is the ingestion rate, how much are you drinking per day, times the exposure frequency, how many days per year are you drinking, times the exposure duration, how many years are you drinking. So we've got basically how potent is it, how much are you drinking per episode, how many episodes per year are you having, and how many years are you worried about. So this is for kind of chronic exposure. You can use this, so you could come up with, in this case, a lifetime. If we took a lifetime as a common red for low-level chemicals, for low amounts that are in drinking water. 70 years times 365 days per year would give you a AT of averaging time of 25,550 days. So this is basically figuring out acceptable levels in drinking water. And I don't know if you've ever noticed this, but if you live in an apartment somewhere in town, Merced City will send you a pamphlet once a year showing you what's in your drinking water. And you'll see a whole list of different chemicals there. Some of them don't look too great. And you might wonder if that's harmful or safe. Well, it's safe according to this 1 in a million calculation. So the acceptable risk up here is where you would typically plug in 1 in a million almost every time, because that's sort of a legal amount. Now, as I mentioned, for non-carcinogens, it's a little bit different approach. So thresholds below which there is no risk happen with non-carcinogens, and but these are determined very conservatively. So they want to make sure you're exposed only well below that threshold. They don't want to just use that threshold as a cutoff, because then it'd be too easy to slip over that threshold and people would be harmed. So they determine this using what they call a reference dose, which is called RFD. And I know these variables have the craziest abbreviations, and that's kind of the epidemiology and toxicology world where they come from. So RFD is the reference dose, and that's the dose that's kind of supposed to be sketched a little bit over here. The idea is that this is supposed to be shown well short of the threshold, which is over here. So we want it safely away from that threshold. A factor of 3 or so, depends on the chemical, but these are determined to be kept well away from the threshold dose. So in this case, we have a hazard quotient for a non-carcinogen, HQ, and this is the average daily dose over the reference dose. And so this literally means that if the hazard quotient is less than 1, that means that your average daily dose is less than the reference dose, then there's not much risk. And if the hazard quotient is greater than 1, then it's greater than the average daily dose is greater than the reference dose. So you're getting close to that threshold, and you might even be, if it's big enough, you might even be past the threshold. So greater than 1 is a significant risk. Less than 1 is not much of a risk. And the borderline is obviously when you get HQ exactly equal to 1. So in this case, for a non-carcinogen, we're going to look at the acceptable risk in terms of this little equation, which is going to be the quotient times the reference dose, which is basically equal to the average daily dose that is right at HQ equal 1. And then that's going to be times the body weight and divided by the IR, which again is back up here, ingestion rate. So body weight and ingestion rate, body weight, reference dose, and hazard quotient. Erase these and then do a little example so we can actually see this stuff in action a little bit. So this example has to do with one of our favorite chemicals in the class, trichloroethene, TCE. So what's an allowable residential concentration for TCE in drinking water? Assume the acceptable risk is what we just said, 10 to the minus 6. So this is for a carcinogen. So let's first talk about a carcinogen. So it'll be a different problem if we're talking about it. It's also a non-carcinogen. It also just makes you ill, but it is carcinogenic. From the EPA IRIS database, which is something we'll also talk about, this is a really good database where you get all this information about these toxic chemicals. And you'll find a pretty involved little report on TCE, and I put a copy up in the box for you to look at, and we'll take a look at it here in a minute. The oral ingestion slope factor is 0.05. this was figured out, I think, with mice or rat studies, that the slope of the line for cancer causation in mice, let's say, was about 0.05. So let's look at an adult male, 70 kilograms, drinking his 2 liters a day. Residential living, the EF, this is all coming now on table 6.14, which is coming from the EPA handbook. So the EPA are the big risk guys. They've figured out a lot of these calculations. So we look at the efficiency factor and the exposure duration and the exposure frequency. So exposure frequency is 350 days per year. I guess they assume there's a couple of days where you don't drink that water. And then the duration's about, so if somebody in an area where there was TCE in the water and you wanted to know what would be their increased likelihood of cancer after 30 years of drinking that water, this is where we would go at it. My eraser again here. And so we go back to our equation that we saw before. Here it is again. Except it's 10 to the minus 6th. Here's our acceptable risk, 10 to the minus 6. Body weight, 70 kilograms. 70 years for a carcinogen. 365 days per year. Is the 70 times 365 days is the amount of years for a carcinogen. The slope factor is from the EPA IRIS database that we found. How much do they drink? 2 liters per day. And then in this case, we're saying, what if they drink it this much? 350 days per year for 30 years. So the acceptable concentration then, in this case, comes out to be 1.7 micrograms per liter.